Your training script says GPU active, but your model might be running at CPU speeds. High utilization metrics can tell a lie that costs you money and time. Developers often assume that if code runs without crashing and logs show device detection, they are leveraging hardware acceleration. The reality is far more deceptive. I/O bottlenecks or configuration mismatches can leave the GPU idle while you pay for expensive cloud compute. In some reported cases involving major frameworks like TensorFlow version 2.3.1, users observed 0% utilization during eager mode sessions despite manual activation attempts, with training speeds identical to CPU execution. This false confidence leads to wasted hours debugging a system that appears functional but is fundamentally stalled. The core of the problem lies in distinguishing between what looks active and what actually computes. A process may appear busy due to data loading or optimizer overhead, while the GPU itself sits idle because tensor operations are not being offloaded effectively. Think of it like a Ferrari stuck in traffic versus driving on an empty highway. The engine is running, the wheels might be turning slightly as you inch forward, but the car isn't moving at its designed speed. In software terms, your CPU acts as the bottleneck, feeding data too slowly for the GPU to process. Or worse, configuration errors cause a software fallback that looks like hardware acceleration on paper, but executes everything in memory where it belongs, only if offloaded correctly. We have concrete evidence of this happening across major open-source projects with tens of thousands of users relying on them daily. In one specific instance within the TensorFlow repository, which boasts over 197,000 stars and nearly 80,000 forks, a user reported that after manually enabling memory growth settings on a Tesla T4 GPU, they observed 0% utilization. The training speed remained identical to CPU execution during eager mode sessions. The hardware was detected as active, yet the actual compute saturation hit absolute zero because tensor operations were not being offloaded effectively despite the environment appearing functional. This is not an isolated edge case. It represents a systemic engineering challenge where successful session initialization does not equate to active compute saturation if data pipelines are bottlenecked. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider another scenario involving the Mask RCNN repository, which has over 25,000 stars and more than 11,000 forks. Users reported that while they successfully initialized sessions on a GeForce 1050, training stalled at epic 1 out of 5 with zero GPU usage visible in standard system monitors. The system detected the device perfectly fine but failed to saturate it due to data pipeline bottlenecks or optimizer overhead specific to their configuration. This creates a dangerous illusion where developers believe they are scaling efficiently when they are actually waiting for slow disk reads or network transfers to feed the accelerator. In another case from the Nerf Studio community, training fell back entirely to CPU processing with 0% GPU load, despite CUDA being installed and required, proving that standard metrics like device detection do not guarantee actual hardware saturation. The stakes here involve direct financial waste in cloud environments where you are billed by the second for compute resources. Mistaking idle compute for active training results in bleeding budget on underutilized GPUs without realizing it until your invoice arrives. You might be paying premium rates for a Tesla T4 or an RTX 3060 Ti, only to have those chips sit at 0% utilization while your CPU works overtime handling the data loading logic that should have been parallelized differently. This is especially true when you encounter what looks like an infinite loop deception where training hangs indefinitely on the GPU but works fine on CPU. In these cases, logs suggest activity and parameters are logged as if everything is proceeding normally, yet no tensor computation occurs past initialization due to driver or environment conflicts specific to certain operating systems. A particularly insidious trap involves confusing memory allocation with actual compute saturation. Historical reports from TensorFlow models revealed a deceptive state where VRAM was fully allocated, using nearly 4.7 GB out of 6 available, and core clocks fluctuated normally. Yet the actual matrix multiplication tasks ran on the CPU at 100% load, while the GPU appeared busy via memory metrics but remained computationally idle. This happens because allocating memory is a necessary step before computation. but it does not mean the hardware is performing the heavy lifting required for model convergence. When you see high memory usage and fluctuating clocks without corresponding kernel execution time or matrix multiplication activity, your data pipeline is likely starving the accelerator of work to do. To diagnose this correctly, you must move beyond simple utilization percentages and look at kernel execution time, memory bandwidth saturation, and CPU to GPU transfer rates. A senior engineer does not just check if a process is running, they verify that the data loader can feed tensors fast enough for the GPU to maintain full saturation during training epochs. If your CPU load spikes while GPU usage remains low or flat despite high memory allocation, you have identified an I/O bottleneck rather than a hardware failure. The debugging mindset shifts from asking, "Is my code crashing?" to, "Is my data pipeline feeding the accelerator at the speed required for convergence?" This distinction separates developers who blindly trust logs from those who can diagnose system-level bottlenecks and optimize their workflows accordingly. The fix requires specific engineering judgment regarding your data loaders, CUDA versions, and QDNN compatibility with your framework requirements. You must verify that you are not accidentally running in a mode where operations default to CPU execution despite GPU availability. Checking for driver conflicts or mismatched library versions is essential because these small configuration errors can cause the entire training loop to fall back to slower execution paths while reporting success metrics. Understanding this distinction is a critical skill for machine learning practitioners who need to separate performance issues caused by code inefficiency from those caused by hardware misconfiguration. In conclusion, high utilization metrics are not always trustworthy indicators of system performance if they reflect memory bandwidth or buffer allocation rather than actual matrix multiplication tasks. Your job as an engineer is to look deeper into the pipeline and ensure that every second build for cloud compute translates into meaningful model training steps. By focusing on kernel execution time and data feed rates, you can stop wasting money on idle hardware and start building systems that truly leverage the power of your GPUs. This level of insight transforms how you approach system design and ensures your engineering judgment remains sharp in an era where computational resources are both powerful and expensive. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.